So in this video, we're going to look at the application of partial derivatives to economic models. So this application exercise, we're going to split it into 4 sections, starting with looking at how we can calculate marginal effects using partial derivatives. We also look at comparative statistics, basically working from the national income and the market models that we have looked at, and then the calculation of elasticity, as well as applying partial derivatives to the Jacobian. So for this session, we'll work through the first 3, and then the Jacobian, we'll do it in the next video. Right. So when we talk of marginal effects, basically what we are calculating is the additional effect that comes through as a result of increasing either the total utility or total output or total quantity by 1 more unit, right? So in the example of a utility function, we are saying we can calculate the marginal effect of increasing x1 by 1 unit on total utility. So if we are given the following utility function, which is basically explained as a function of x1 and x2, right? And the question now is to find the marginal utilities with respect to x1 and x2, right? So marginal effect, it's all about differentiating the utility function with respect to either x1 or x2. So in this case, because we have got more than one independent variable, when we want to calculate the marginal effect or the marginal utility of x1, we have to partially derivate the utility function with respect to x1, right? So we can write our functions as the partial derivative of u with respect to x1 will give us the marginal utility of x1, or the partial utility with respect to x2 will be equals to the marginal utility for x2, right? So when we look at our function, right, there's 2 functions in it, right? The first one, you see that it only has x1, and then the second one only has x2, right? So going back to the different methods or the different rules of differentiations that we have worked through, one can easily be tempted to think of the product rule in this application. But if you recall, we applied the product rule when we have got 2 functions being explained by the same variable that we want to differentiate with respect to. So ideally, if we had x1 in this bracket and also x1 in this second bracket, then we would think of the product rule. But what we know is when we take a partial derivative, right, with respect to one of the independent variables, the other independent variable will be behaving like a constant. So basically what we have there is we have the first bracket that has got x1 in it, and then the other bracket will be a constant, right? So we can rewrite the utility function, right, introducing a new variable w to capture the elements that are inside the first bracket, right? So we can rewrite the utility function as w squared multiplied by x squared plus 3 raised to the power of 3, which is behaving like a constant. So in this instance, your w is basically your x1 plus 2, right? So what we're showing there is we are going to apply the chain rule to calculate the marginal utility of with respect to x1, right? So proceeding to apply the chain rule, what we need to calculate for us to find the partial derivative of u with respect to x1 is to calculate the partial derivative of u with respect to w multiplied with the partial derivative of w with respect to x1, right? So for the first element, partial derivative of u with respect to w, this is a constant, right, multiplied by the derivative of w, which is going to be 2w, right? And then we multiply this answer to the partial derivative of w with respect to x1, which is from this function, which is 1, right? So as our solution, we have to bring back the elements that represent W, right? So that our marginal utility function is expressed in terms of x1 and x2. So we can now say our marginal utility with respect to x1 will be equals to 2 times x1 plus 2 multiplied by x2 plus 3 raised to the power of 3, which was our constant. Right. So same applies. If we want to find the marginal utility for x2, it means the first bracket will be behaving like a constant, and then you apply the chain rule on the second bracket, and it's bar. All right. We can also apply partial derivatives or partial differentiation in what we call comparative statistics, right? So if you recall in topics 1, 2, and 3, we were basically solving for the equilibrium solutions, right? And we gave examples of the national income model as well as the market model, right? So starting off with the national income model, remember we had systems of equations which we basically showed how to solve for the equilibrium solution, either using substitution and elimination or using matrices, right, with either the Cramer's rule or the inverse method, right? But the solution that we're going to get there was your Y star, your C star, which are basically solutions for the endogenous variables, right? So now with the comparative stats, what you're basically doing now is doing an analysis further to you ascertaining the equilibrium solution. So you need to find the equilibrium solution first, and then you can do the comparative analysis. So with the comparative analysis, now what you are doing is you are finding the effect of changing the exogenous variable on the equilibrium solution of the endogenous variable, right? So as an example, let's look at this national income, where your income is basically a function of consumption, investment, and government expenditure, right? We are also given a consumption function, which is basically a function of disposable income. And then we also have a tax function, which is a function of income, right? So in this case, we can identify the two endogenous variables as your Y and your C. And then all the other elements, your I, G, A, B, C, and D, are your exogenous variables. And the biggest assumption that we are making is that the exogenous variables are independent. So when you change one of the exogenous variable, it will not affect any of the exogenous variable. It can only affect the endogenous variable, right? So using substitution and elimination, we are able to find the equilibrium value for Y. In this case, that will be your Y star. So what we need to do is to substitute back, right? So in the consumption function, we substitute for T, and then in the income function, we are going to substitute for C, right? So you see your Y now becomes your A plus B times Y, right? It's coming from the consumption function there, minus Y, A plus B multiplied by Y minus the T. The T we have substituted for the text function that is given there, then plus your I plus G. So what you simply need to do is to open the brackets, isolate your Y, right? Take your Y to the left-hand side of the equation, and then factor out the Y, and then we end up with the equilibrium solution, right? Once we have established the equilibrium solution, we can now do comparative analysis on the equilibrium solution. We are basically asking ourselves, what's the effect on your equilibrium solution Y star of changing either A, B, C, I, or G, right? So if we are looking at the effect of changing G, changing government expenditure, right? You are basically assuming that all the other independent variables, your exogenous variables, are being held constant. So there's that ceteris paribus assumption that you are already working with, right? So because our function of y star is made up of a number of exogenous variables, what we want to find is the partial derivative of y star with respect to g, not the total derivative represented by the letter d. Okay, so keeping in mind our equilibrium solution, we are basically going to be differentiating that equilibrium solution, right? So to isolate the effect of a change in G, right, we have to understand that all these other elements are behaving as constants, right? So there is no way we can apply the quotient rule on this one because G is only in one of the elements, right? So we can actually rewrite the equilibrium solution in a linear equation, right? Where you can actually see that what we have is 4 different elements that are attached to the constant 1 over 1 minus b plus bd, right? And because these other 3 elements do not have a g in them, it simply means they are constants when we want to isolate the effects of a change in G, right? So when you differentiate that function, partial derivative of y star with respect to G, it will work out as 1 over 1 minus b plus bd, because this is the constant that will be attached to this G. And this G is raised to the power of 1. So when you differentiate it, the answer will be the constant, right? And we interpret this solution as the government expenditure multiplier, right? In the same manner, we can also find the effects of the other exogenous variables. So for instance, we want to find the effect of change in C, right? Recalling that C, it is the non-income tax multiplier in our tax function, also known as the autonomous taxes, right? So with the C, if we are to go back to our solution, we can see that there is minus b over 1 minus b plus bd that is attached to the C, where this first component basically is a constant, right? So if you are to differentiate that, you end up is with minus b over 1 minus b plus bd as your solution, right? We can also talk of the value itself, whether it's a positive or negative value, because we understand the behavior of all these unknowns that are in the equation. So going back to the original systems of the equations that were given in the example, we already know how these coefficients are behaving, right? So b, it's a fraction, b, it's a fraction, d, it's a fraction, right? So if you are to simplify this, minus a fraction over 1 minus a fraction plus fraction times fraction, the final solution is definitely going to be less than 0. So we know that this non-income tax multiplier, it's a negative. Okay. Now looking at another example, we can actually also calculate the income tax multiplier. What's the effect on your equilibrium income of increasing your your income tax multiplier? All right. So when you go back to the solution, D is in the denominator, right, of this solution that we have ascertained for our equilibrium income, right? So looking at this, you can also be tempted to think that maybe we can use the quotient rule to solve this, but because we don't have D in the numerator, right, what we have to do is to rearrange the equation and allow ourselves to use the chain rule to solve it, right? So as we rearrange it, the whole elements of the numerator, we know that they are constants, right? And then the denominator is going to be in another bracket raised to the power of -1. So we can apply chain rule there, but there is a constant attached to that problem, right? So if you do your calculations correctly, the partial derivative of income with respect to D is going to be minus B multiplied by that. All right. So simply saying that as you increase your income tax multiplier, so as you increase your income tax, that is going to reduce the equilibrium income. Applying it to the market model, your demand and supply, we also recall from topic 1 and 2 that we can solve for the equilibrium solutions. In this case, that will be your QD star, QA star, and your P star. And if you recall the solutions, we found out that your P star is going to be A plus C over B plus D, and your Q star will be AD minus BC over B plus D. So we can do the comparative statics on these two solutions where we can calculate the effect of a change in C on your P star or your change in D on your P star. So if you change A, in this case, change in A on P star is the partial derivative of P star with respect to A, and the solution is going to be 1 over BD. Same applies with your change in C. Your answer will be 1 over BD, right? So basically you're saying if you change these two values, that is actually going to cause a similar effect on your price, right? It's a positive effect on your prices. And then if you look at the other elements, your change in B and your change in D, you basically have to use your chain rule to solve that. And the solutions are also going to be the same for those two changes, change in B and change in D. And if you have to compare the movement of price when A and C are changing and the movement of price when B and D are changing, you see that they are moving in opposite directions. All right. We also apply the partial derivatives to elasticities, right? Calculation of elasticities, right? So now what you are seeing is we have a demand function that is basically explained by three variables: on price, that's P1, the price of other good, that's P2, as well as the income. So when you calculate the on price elasticity, which is E11, you're going to basically calculate the partial derivative of the demand function with respect to P1 multiplied by the price P1 over Q1. And then if it's cross price elasticity, you're looking at the change in Q1 when the price of the other good is changing. So it's partial derivative of Q1 with respect to P2 times P2 over Q1. Right. So in this case, as you can see, there's no sign attached to it, unlike with on-price elasticity. On-price elasticity, we already know about the inverse relationship that exists between price and quantity. But with the cross price, it depends on the type of good that you're working with. Is it a substitute or is it a complement? That will determine the sign that you have on your changes. With income elasticity, you're looking at the change in Q1 as income changes, right? So you take the partial derivative of Q1, your demand function for good one, with respect to Y, multiplied by the Y over Q1, right? So with the income elasticity as well, we have got three possible outcomes. We know that if elasticity is greater than 1, then it's a luxury good. If elasticity is less than 1, it's a necessity. Then if your elasticity is less than 0, then we are looking at an inferior good. All right. For a necessity, it has to be less than 1 but greater than 0. Right. Looking at an example, if we are given the following demand function, which is a function of P1, P2, and P and Y, given as 12 minus 4P1 plus 3P2 plus 0.1Y, we can calculate the 3 elasticities. So we are also given additional information that P1 is equals to 2, P2 is 4, Y is equals to 200. Right? So to calculate your on price elasticity, right, remember the negative sign, we are going to get the change in Q1 over change in P1 multiplied by P1 over Q1, right? So we are getting partial derivatives of the Q1 function with respect to P1, right? It's a linear function, so all the other elements will be behaving like constants. And the only part that we are differentiating is where we have minus 4P1, right? So we substitute for P1 and Q1 from the given values, right? So in this case, we are given P1, but we don't have Q1, right? What we are basically going to do is we take this information, plug it back into the demand function, and then we can solve for Q1. And if you do it correctly, your Q1 comes out at 36. We can also calculate the cross price elasticity, differentiate the Q1 function with respect to P2, right? And multiply with the price and the quantity, right? So in this case, you can see that the value of our cross price elasticity is positive, right? So because it's positive, then we know and they are substitutes. With the income elasticity, right, we take the partial derivative of the demand function with respect to income, right? And then we substitute for income as well as quantity. And in this case, it's a positive value that is less than 1, right? So because it's less than 1, it means it's a necessity. All right.